Alright, so for extension 1 today, we're going to learn this new principle called Pigeonhole Principle. Before I explain what the principle is, I think it might be better off if I ask you this question. Alright, I want to ask you a question. Let's say I have a bag with 3 pairs of different colored socks. So you have 2 red socks, 2 blue socks, and 2 white socks. Okay? My question is, how many socks do you need to pick out of this bag blindly to guarantee or make sure you pick 2 of the same colored socks? Okay, that's the question. Okay? Is it 2 picks? If I chose 2 socks out of the bag, let's say I chose red. If I'm lucky, I might choose another red, but that's not a guarantee. I could choose another color for my second pick. So picking 2 socks out of the bag isn't enough for me to guarantee that I'll pick 2 socks of the same color. All right? What if I made 3 picks? So once again, my first pick could have been red. My second pick could be any other color. And my third pick could be any other color as well. There's no guarantee that I'll pick the same color as what I've chosen in the first 2 picks. So let's say on my third pick, I was still unlucky and I chose a different colored sock. All right? But after 3 picks, after choosing the worst case scenario where I've chosen a sock with different color of each, for my 4th pick, I'm guaranteed to be choosing a sock that matches with one of these colors that I've chosen so far. So my 4th sock could be red. So for my 4th pick, I'm guaranteed to pick 2 socks of the same color. All right? So that's what Pigeonhole Principle is. If you want to know the number of picks to guarantee you to get 2 of the same thing, notice how here we have 3 colors. Okay? Obviously blue, red, and white. Right? So the number of picks required is actually the number of colors plus 1, okay? Which is 4, like I've said. So this is what we're going to apply to different types of questions. Let's have a look at example 3a using the same concept. So a bag contains green, black, yellow, white, and red, and blue jelly beans. How many jelly beans must Kira take out of the bag so that she is sure to take 2 of the same color? All right, so I've written the colors here. Now, I just want to clarify with this question. This doesn't mean there are only 1, 2, 3, 4, 5, 6 jelly beans. There are a lot more than that. So for instance, this question could mean there are 3 greens, 10 blue, 3 yellow, and etc. All right? So once again, girls, the technique here is there are 6 types of colored jelly beans. So in order to make sure that you pick 2 jelly beans of the same color is the number of colors plus 1. Okay? So 7 picks. And once again, the explanation is you always think about the worst case scenario. Let's say on your first 6 picks, you chose 1 of every different color. So you haven't chosen any of the same colors in your first 6 picks. But after choosing all of the different types of colors, the extra 1 jelly bean that you pick after all that, you're guaranteed to pick 1 of the same color that you've chosen in your first 6 picks. Okay? So that's what Pigeonhole Principle is. So let's have a look at this question here. All right? So let's say, for instance, I have 4 pigeonholes. The question is, how many pigeons do I need so that one of the holes is guaranteed to have at least 2 pigeons? Okay? The answer is, just like what I've been doing, 4 holes plus 1, which is 5 pigeons. And the reason is, girls, let's say the first 4 pigeons all decide to fly inside one of these holes like this. Okay? So we've got 4 pigeons here. Now, if I have 5 pigeons, that last 5th pigeon has to go into one of these holes, sharing a hole with another pigeon. Let's say it was in here. Okay? So as you can see, we have 2 pigeons in one of the holes. Obviously, in real life, this may not be the case. You may have 3 pigeons sharing one hole, or even 4 pigeons sharing one hole, and etc. Obviously not likely, but we know there's always going to be at least 2 pigeons in one hole when you have more pigeons than the number of holes available. Okay? So that's Pigeonhole Principle. If you want to know how many picks or how many objects you need to get 2 of the same kind, just add 1 to the number of holes or the number of kind. So let's apply the same concept for example 3b. It says, is it certain that at least 2 students will have the same birthday in a school with 750 students? All right, so the trick here is, girls, let me rephrase that question. Let's say you were hosting a party and you wanted to know how many guests you need to invite to guarantee that you have at least 2 people with the same birthday. To start this off, girls, let's say this is your list of people, the number of people that you invited. We know there are 366 days in a leap year. So that's all the possible dates in the calendar you could possibly have. So if you invite 366 guests, okay, let's assume the worst case scenario. Let's say these people all have different birthdays. So that means you've used up all the single possible dates of the calendar. So after 366 guests, if you invite one more person, this person is certain that person is going to have the same birthday as one of these 366 people. Yeah? Because we've used up every single birthdays possible within these 366 people. Adding an extra person will guarantee 2 people with the same birthdays. So the answer is 366 plus 1, which is 367 guests that are required to have at least 2 people with the same birthdays. Okay? All right, let's have a look at example 3C. So a paragraph contains 33 words. Show that there must be at least 2 words that start with the same letter. All right, there are 33 words in a paragraph. Okay, with this one, the way to start off with this, there are 26 letters in an alphabet. So if I have 26 words in a paragraph, worst case scenario, every single one of these words starts with a different letter. Yeah? So if I've exhausted all that up, anything more than 26 words, so plus 1, if I have 27 words, I am guaranteed to have at least 2 words that start with the same letter. Yeah? Hope that makes sense. All right, so now let's have a look at a trickier question. Let's have a look at question 5 from Fitzpatrick. Right, so question 5, I thought it was an interesting problem. It says 25 students attend a class reunion and shake hands with each other. If no students shakes hands with the same person twice, explain why 2 students will each have shaken the same number of hands. Okay? All right, so to start this question off, girls, out of the 25 people, let's take one person out. How many handshakes will one person make? The answer is 24 handshakes, because you're not going to shake your own hand. You're shaking 24 other people. So that's how you set this question up. So there are 25 people, and you're trying to essentially see this question as trying to fit 25 people into 24 holes, just like the Pigeonhole Principle here. So obviously if there are 24 holes but we've got 25 people, which is 1 more than the number of holes here, let me just draw 24 holes. We've got 25 people to fit in these 24 holes, and because there's 1 extra person, we're guaranteed to have at least 2 people sharing 1 hole, which implies there are going to be at least 2 people with the same number of handshakes. Okay, so that's how you do this problem. Okay, so for the next part of the Pigeonhole Principle, we're going to have a look at a more generalized principle. All right, so it says basically, and I've reworded this to make it easier to understand, if you have more objects represented by the letter N than the number of holes by letter K, then one of the holes, or at least one of the holes, must contain at least N over K objects. So what that means is basically going back to our same example from the other side of the board. If there are 4 holes and 5 pigeons, okay, then that means in one of those holes, there's gotta be at least 5 over 4 pigeons in one hole. So what that means is if you put 5 over 4 in the calculator, you get 1.25. Now you can never obviously have 1 and 0.25 of an object or thing, or like living things. So you always round up. So this generalized principle basically says you're always going to have at least, in this case, 2 pigeons in a hole. Okay, so this basically helps you calculate the least number of things that will be inside one of the holes if you have more objects than the number of holes. Okay, so let's apply that in example 4a. A group of 75 people in a singing contest are placed into different audition rooms. So you've got males, females, children in groups. If there are at least X people in one of the rooms, find the value of X. All right, so the way to look at this problem is there are 75 people and you've got male, female, children in groups. So there are 4 holes. That's the way to look at this question, okay? So the question is, like I've done previously here, how many people is there going to be at least in one of these holes? Okay, the least number of people. And to do that using the principle, it's just 75 divided by the number of holes. And whatever number you get, you always round up. So there's going to be at least 19 people in one of those holes. Okay? Obviously, you can always have more than 19, but that's the least number of people that there always be in one of those audition rooms. Same thing for example 4b. A group of 117 people rated a TV show from 1 to 5. Find R if there were at least R people who gave the same rating. So this is basically the same question. You've got 117 people, and because there are 1 to 5 rating, that means you have 5 holes. So each of these holes represent obviously the rating from 1 to 5. So they're asking how many people would always have, what's the least number of people that would have the same rating. So it's just the same thing, 117 divided by 5. And if you put that in the calculator, so obviously round up, so there's going to be at least always 24 people that give the same rating. All right, so now let's have a look at question 12 in the actual exercise. Bit of a tricky question. Question 12. The numbers 1 to 30 are divided by 7. And the remainder is recorded. Find the value of X if at least X of the numbers between 1 to 30 or 1 to 30 have the same remainder. Okay, so we want to know how many of those numbers share the same remainder when it's divided by 7. So here's how to set this up. So you've got all the numbers from 1 to 3 all the way to 30. And the thing that you got to know, so these are my objects, okay? And the next thing you got to know after you get your objects or the number of people, like our previous questions, is to figure out how many holes there are. And the holes are actually represented by how many remainders we can possibly have when we divide by 7. Okay? Remainder, and that's the holes. Okay? And these are the objects. So if you divide by 7, what remainders can you get? You can get a remainder of 0 because any multiples of 7, if you divide by 7, there'll be no remainder. You can have a remainder of 1, 2, 3, 4, 5, 6. Not 7 because you're dividing by 7. So as you can see, we have 1, 2, 3, 4, 5, 6, 7 holes. So the way to do this question is we've got 30 objects, we've got 7 holes. So the number of numbers that will always have the same number of same remainder in common, it says 4.3, round up. So there'll always be 5 numbers at least that have the same remainders. Okay? Just a little confusion that might arise from this question is, well, if we're only talking about numbers that can be divided by 7, shouldn't we just count the numbers from 7 and onwards? That's what I thought, but that's actually not the case. You can actually do 1 divided by 7, which is just 0 remainder 1. Okay, so numbers less than 7 can be divided. Okay, so similarly for 2, if you do 2 divided by 7, that's 0 remainder 2. So keep that in mind. That's why we're including all the numbers, not just from 7 onwards. Okay, so I have one final question to go through with you girls. Let's go back to example 4b. What if the question was a group of certain number of people that we don't know rated a TV show from 1 to 5? If there were at least 24 people that gave the same rating, how many people rated the TV show? So in other words, we don't know that number 117. So the question is, if there are n people, and we know there are at least 24 people that gave the same rating from 1 to 5, how many people were there? So in order to do this question, girls, so you have to work backwards. So what you do is, going back to this, N is the number of people we're trying to look for. K is the number of holes which you know is 5. Okay? Now here's the tricky part. This number has to be greater than the one less than 24, 23. The reason why you round down is because remember this 24 came from the number that we rounded up. So in order to work backwards, you write 23, not 24. Okay? And the reason why it has to be always greater than that, because as you can see, this fraction is 23.4. It's bigger than 23. So this is your setup whenever they give you a question where they don't give you the number of people. If they say the number that has the least amount of, you always take the number one below, and then you just work backwards. So you just have to times across. So that means keeping the inequality sign, 5 times 23.